Hey class, welcome back to our lesson on similar polygons. So we have this whole unit that we're working with. This is the second video that we're using about similar polygons. In the previous video we talked about understanding similarity and how it works. And in this video we're going to talk about scale factors and similar polygons. So hopefully we get a couple of good concepts across. So we jump right in with an example, and this plays off of the previous lesson, not the previous video, but the previous lesson about ratios and proportions. So we have to recall how ratios and proportions worked, so that way we can deal with figuring out some stuff when it comes to scale factors and similar figures and all sorts of neat stuff. So here's a problem that we will begin with, and again, it's pretty straightforward from what we worked with in the past. So this is about how we use a scale drawing, and it'll help us with what a scale factor is. So the diagram shows a scale drawing of the Golden Gate Bridge in San Francisco. The distance between two towers is the main spans. By the way, there's the rest of the words. So the distance of the two towers is the main span. What is the actual length of the main span of the bridge? This is what we know. The scale is at 1 centimeter is equal to 20 meters. So we're going to figure out what is the actual length from the two towers. Okay. So what we have to do first is measure the distance in centimeters. If we know we're talking about centimeters to meters, we can set up a ratio, just like we have heard from the previous lesson. And so we know the ratio we're going to deal with is centimeters to meters. Okay. And so what we have to know is that we have 1 centimeter is relative to 200 meters. So how are we going to figure out the actual length based off of this drawing? We should probably know how many centimeters it is from tower to tower. And this is where measuring tools come in handy. So we can take our handy-dandy protractor and measure the distance from tower to tower. And it looks like it's going to be from one tower to the next, right here, which is about 6.9 centimeters. And let's not be afraid of that number. It's 6.9 centimeters. So from one tower to the next is 6.9 centimeters. We're going to figure out how long the actual bridge is. Okay, so how do we figure that out? Well, remember from the previous lesson, we can use a proportion. So we know that we're dealing with centimeters to meters, and we know that the scale factor is 1 centimeter to 200 meters, and that's going to be equal to, well, in this case, 6.9 centimeters to some actual length in real meters. Okay, so we're going to have to figure that out. And so what do we know? We know since this is a scale factor, we're going to have equal ratios, which means we have a proportion. So we have a proportion. Okay, so this is what we have. We have some kind of neat equation here. Okay, so we can cross multiply, use the cross products, just like we've done in the previous lesson. So if this is all unfamiliar to you, you must stop here and go back to the previous lesson on ratios and proportions, and I believe this would be video 3. Okay, so we have to remember how cross products work. So the product of the extremes is equal to the product of the means. So we can make even a prettier equation, shall we? So we have 1 to 200 is equal to 6.9 to x, right? And so we can cross multiply and divide. So 1x would be equal to 6.9 times 200, and we could use a calculator if you'd like. I mean, I could probably do this in my head, but I'd rather not. 1380 would be the result. So there is our results. So what does this mean? We have to understand what this means. So 6.9 with a scale factor of 200, right, would result in 1,380 meters. Okay, so we're using scale drawings, we're understanding scale factor, and we're picking up where we left off, because what does this mean? This means this model is a similar figure to the actual bridge. Okay, so this model is a similar figure to the actual bridge, and we want to we want to make sure we understand that because it's going to help us lead into similarity when we get to crazy stuff. So here's another example. What would be the actual height of the towers above the roadway? So once again, we're going to figure out some stuff. If this is a model, right, a scale drawing, so it's a similar figure to the actual bridge, we should probably know how many centimeters is a tower. So we can measure, use our handy dandy measuring tool, and it looks to be about 1.3 centimeters, let's just say. So it's 1.3 centimeters, and again we're using the same ratio, centimeters to meters. And the scale still is 1 to 200, and so that's going to be equal to 1.3 to some actual length. Okay, so again, how do we figure that out? And once again, just like in the previous lesson, cross products. So what does this mean? We have similar figures. Now, why is this important? I'm going to show you in a second because of the previous notes. So these are cross products, and then, of course, 200 times 1.3, and again, cheating with a calculator. I don't feel like doing that in my head right now, if you don't mind. So it would be 260 meters. So the height of one tower is 260 meters. So why are we doing this now? Because if you remember from the last note, when we have similar polygons, we have corresponding sides that are proportional. Okay, so with similar polygons, we have corresponding sides that are proportional. So it's important to highlight that right now. We're setting up a proportion. Okay, so the 1 centimeter in the model is 200 meters to the real thing. They are similar figures. So that's how we're kind of bridging the gap. We're bridging the two lessons. The previous lesson on ratio and proportions to similarity. Now, how does that work in a problem like this? So we recall the note from the previous video on similarity, and here we have two different shapes in a diagram, and we want to know, are the polygons similar? And if they are, we're going to write a similarity statement and give this the scale factor. Now, the first thing I want to emphasize is that I disagree. Just Mr. Katz disagrees with the use of that word scale factor. The textbook does. The scale factor you can't determine from here. You have to find the ratio first. Each figure has a scale factor based off of the proportional ratio. So I would rather this had said ratio, but I want to be clear that I disagree with the textbook. Doesn't mean the textbook's wrong. I'm just saying it's confusing. Scale factors are clearly how much something grows or shrinks, not when you compare one thing to another. But anyway, that's just me versus the book. So we want to go back to that note from the previous lesson. How do we know if we have similar polygons, if corresponding angles are congruent, and if the sides are proportional? So angles congruent, sides proportional. Now we look at these two diagrams, and we can see, hopefully, that we have corresponding angles. U to K, T to J, W to M, and V to L. Are the angles that correspond congruent? Right? Absolutely yes. So the angles are congruent. We have that. So that checks out. But now the question is, are the sides proportional? So what does that mean? If you recall from the last video, we were talking about knowing proportional sides. So we know that TU and JK make a ratio, right? So from TU to JK, we have 6 to 12. And if it's proportional, we would have equal ratios all around. So that means that then TW would have the same ratio as JM. So TW is 6 and JM is 6. And right now, we could stop, but we could keep going, just to emphasize stuff. Is that proportional then to UV, which is 16, compared to KL, which is 24? So is that comparative? Right? And then finally, our last proportional side, 14 to 24. So are all these ratios equal? Do we have a proportional statement in this case? And that's what the question is asking. Yes, the angles are congruent, but are the corresponding sides proportional? Do we have equal proportions? Well, let's simplify everything and make your life easier. So simplify all of this to tell. Okay, so let's simplify everything. 6 to 12, hopefully you should know by now, is 1/2. 6 to 6 is 1. 16 to 24 is, let's see, both of them are divisible by, what, 8? So 2/3. And then 14 to 24, both of them are divisible by 2, so 7 to 12. Is that all equal? So the answer is, of course, no. These are not equal. So what does that mean? That means this is not proportional. Let me use same tense, proportional. Okay, so it's not equal, therefore it's not proportional. So our corresponding sides are not proportional. Okay, sides are not proportional. So guess what we do not have? We do not have similar figures. So no, not similar. Okay, so these are not similar. Ta-da! So we don't have to worry about, in this particular example, what I don't agree or disagree with. Okay, so that's how we can determine similarity. So what about this? What if I gave you another example? Okay, so now we're going to talk about corresponding sides and corresponding things. Now, clearly, if you look at these two, triangles, they're not in the same direction. It's more difficult to tell similarity. So what I'm going to do is redraw the bigger triangle to make it kind of similar. Okay, so in the smaller triangle we have ACB. I'll leave that. Now A has the 2 arc marks, so D has the 2 arc marks here. I'm going to redraw it with the D here. B has 3 arc marks, and here E has 3 arc marks. I'm going to redraw it here, which leaves F down here. Okay, so now what I'm going to do is relabel everything. So from D to F is 10. This is 10. From F to E is 20, this is 20, and from D to E is 15, this is 15. So that way I can tell similarity a little bit easier. So now I can look at these two triangles to help answer the questions. Do we have congruent angles? Right? Angle A, angle D, angle C, angle F, angle B, angle E. Yes, angles are congruent, so we're good. Next we want to look at our proportionality statement. Okay, so if these are congruent, what about from AC to DF? We have a ratio there, right? AC is 8, DF is 10. So we set up our ratio. We have 8 to 10. The question is that equal to the other corresponding sides? Okay, so now we can look at A to B is 12, D to E is 15. Is that a true statement? We don't know. And then our last side, is that going to be equal to the last proportion? From C to B is 16, and from F to E is 20. Does that equal 16 to 20? So it's going to be hard to tell. Okay? So it's going to be hard to tell. So is this a true statement? Well, remember what we done in the previous thing. Let's simplify everything to make sure that we know. So we simplify everything. 8 to 10, both are divisible by 2. So that would be 4 to 5. All right, is that going to be equal to 12 to 15? Both are divisible by 3. So that would be 4 to 5. Hey, so far so good. And then lastly, 16 to 20, both are divisible by 4. So that would be 4 to 5. Check. These are proportional. Yes. Proportional. Proportional. Okay? So when the question asks, what's the scale factor? That's where I disagree with it, and I'll explain why in a second. We should be asking, what's the ratio? So yes, these are proportional. The ratio is 4 to 5. Okay, that's not the scale factor. And let me explain why. If the ratio is 4 to 5, this triangle has a scale factor of, or at least of this length of 3, and this side has a scale factor of 2, and this side has a scale factor of 4. Okay, so each triangle, each side has a different length. But either way, the ratio that we're looking at, or the scale factor the book says, and I disagree with it again, is 4 to 5. So that's the ratio. So that's what it means if they are similar. What's the ratio? Yes, these are similar triangles because the angles are congruent, the sides are proportional, and the ratio is 4 to 5. Okay, so that's how that works, and we'll do one more example and call it a day. So make sure we see. So here's another example. Here we go again. We have Two polygons, are they similar? And if so, we're going to write a similarity statement. Okay, so first of all, what's happening here? In the first polygon, we have a shorter side and a longer side, right? The shorter side is up top, the longer side is on the side. And what's happened in the second polygon? Well, we have a shorter side on its side, the longer side is up top. So again, like I've done before, I want to rewrite it so I can tell correspondence. I want 15 here, and I want 20 on the side. Now we know they're rectangles, right? So we have parallel sides and opposite sides are congruent. So we know that from x to y is 15, so I can rewrite this x to y. And if that's the case, then from x to w is 20, and from y to z is 20. Okay, so we have all of these things we can set up proportionality. All right, so now we have all of our correspondence set up. Are the angles congruent? Absolutely. All angles are 90, so angles are congruent. Do we have proportionality? Okay, so if we look at the short side, KL to XY, 10 to 15, what's happening there? So is 10 to 15 the same as 15 to 20? 15 to 20. And that is the question. So how are we going to answer it? Let's simplify. Okay, 10 to 15, both divisible by 5. So we have 2 to 3. And 15 to 20, both divisible by 5. We have 3 to 4. Okay, so in this case, it is not looking very proportional, right? Now, there's another way that we can tell that these may or may not be proportional. I hinted at this before. What if we looked at short to long? Okay, so if I look at each one short to long, which means I want to compare polygon KLMN, and I'll compare it to polygon XYZW. So if I look at the short side at KL to MN, I get 10 to 15. And if I look at the short side to long side, I have 15 to 20. I have the same proportion no matter what. Okay, so if I compare this one to this one, I have 10 to 15. Or if I compare this side to this side, the same one, I have 10 to 15. So no matter how I set it up, I'm still looking at proportionality. And no matter how I set it up, I'm still looking at 2 to 3 being equal to 3 to 4, which in either case, not proportional. So no, these are not proportional. No, these are not similar. Okay? So not proportional, not similar. And so that is understanding and using similarity to drive our point home. So hopefully that helps when we talk about similar polygons. I'm going to stop the video here and we'll continue the last part of the lesson later.